Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to take up the first numerical on Gram-Schmidt orthogonalization. Let me read out the question first. Consider the signals S1 of t, S2 of t, S3 of t and S4 of t as shown below. Use Gram-Schmidt orthogonalization procedure to find an orthonormal basis for this set of signals. If you look at the signals carefully, S1 of t is defined over the interval 0 to t by 3, S2 of t is defined over the interval 0 to 2t by 3, S3 of t is between the interval t by 3 to capital T and S4 of t is between 0 to t itself. Please note all of them have the same amplitude which is equal to 1 over the intervals wherever they are defined. So, let us start with the solution part. We know that the Gram-Schmidt orthogonalization has two stages. The first stage is to find the linearly independent signals from the given set of signals. Let us start with that first. Now, to find the set of linearly independent signals, we need to analyze the given signals carefully and try to find if any one signal can be expressed as a linear combination of the other. For example, by analyzing the given signal set for this numerical carefully, we find that the signal S4 of t can be expressed as a linear combination of S1 of t and S3 of t. How? If you come back and check S1 of t, it is defined over the interval 0 to t by 3, whereas S3 of t is defined over the interval t by 3 to capital T. So, when I add them, the overall interval becomes 0 to capital T. Since all three of the signals have the same amplitude, we can now say that S4 of t is a dependent signal. Right. Now come back and now analyze the remaining three signals and try to express one of them in terms of other. By analyzing the given signals S1 of t and S3 of t carefully, we find that it is not possible to express one using the other two. Therefore, we can now conclude that the remaining signals, which is S1 of t and S2 of t and S3 of t, they form a linearly independent signal set. Therefore, at the end of stage 1, we now conclude the number of orthonormal basis functions required to express the given four signals is equal to the number of linearly independent signals at the end of stage 1, and for this case it is equal to 3. Right. That is the end of stage 1 of Gram-Schmidt orthogonalization. Now we move on to stage 2, where we find the basis functions themselves. Let us start. We should note that the first basis function is always given by the expression phi 1 of t equals S1 of t divided by S11, which is also equals to S1 of t divided by square root of E1, where E1, which is equal to the energy of signal S1 of t, is given by the expression 0 to capital T S1 square of t dt. This is equal to integral. Come back and check the interval for S1 of t, it is 0 to t by 3. So, the integral limits now reduced to 0 to t by 3. The value of S1 of t over that interval is 1. So, it is 1 square dt. So, this simplifies to, this is the answer for the energy of signal S1 of t. So, I will go back to the equation for phi 1 of t, let me call it as equation 1, and I will substitute the new expression for E1 into equation 1. So, the first basis function is given by phi 1 of t equals S1 of t divided by square root of E1 equals S1 of t over the interval is given by 1 divided by square root of the value of E1 is t divided by 3. So, the answer for this is square root of 3 divided by t. However, you have to be very careful while defining the basis functions, because the basis functions must be defined over a certain duration. Now, since S1 of t in equation 1 numerator as well as E1 are both found for a value of t varying from 0 to t by 3, I have to now introduce the interval for phi 1 of t as 0 less than or equals to small t less than or equal to t divided by 3. This is the answer for the first basis function phi 1 of t. Let us now move on to find the second basis function. To find the second basis function, we define an intermediary signal g2 of t as g2 of t is equal to s2 of t minus s21 into phi 1 of t. Let this be equation 2. With such a definition for g2 of t, we can now define the second basis function as phi 2 of t equals g2 of t whole divided by square root of integral 0 to capital T g2 square of t dt. Please note, this is very similar to the phi 1 of t, but now instead of using s2 of t, we have used the intermediate signal g2 of t for finding phi 2. Let me call this as equation 3. Now, let me substitute equation 2 into equation 3 and simplify it. So, the equation 3, which is the second basis function equation, reduces to s2 of t minus s21 into phi 1 of t whole divided by square root of e2 minus s21 square. Let me call this as equation 4, where s21 is given by the equation integral 0 to capital T s2 of t into phi 1 of t dt. Now, to simplify this expression, you have to find out what are the time ranges for s2 of t and phi 1 of t. We previously calculated phi 1 of t, and phi 1 of t is defined over the range 0 to t by 3, whereas s2 of t is given over the range 0 to 2t by 3. So, the integral limits now should be split. So, I can write it as let us now substitute the values. It is integral 0 to t by 3. S2 of t over the integral 0 to t by t is actually 1. Phi 1 of t over this interval is equal to square root of 3 divided by 3 plus, then we have t by 3 to 2t by 3. The value of S2 of t over this interval is once again 1, whereas the value of phi 1 of t over this interval is 0. Therefore, this simplifies to right. This is the answer for S21. Now, going back to equation 4, we find that there is another unknown term at the RHS, which is E2, where E2 is the energy of signal S2 of t. So, I can now write this as E2 equals integral 0 to capital T S2 square of t dt, but S2 of t is defined over the interval 0 to 2t divided by 3, and the value of S2 of t over that interval is 1, and then we will have dt. So, this is equal to 2t divided by 3. This is the value of E2. So, let us now substitute the values of S21 and E2 back into equation 4. So, it is phi 2 of t equals S2 of t minus S21 is given as square root of t divided by 3 into phi 1 of t divided by square root of, we have E2 which is 2t divided by 3 minus of S21 is square root of t by 3, but there is S21 square. So, it will be t divided by 3. So, this simplifies to, let me call this as equation 5. Now, coming to equation 5, we have some very interesting changes to note. First and foremost, the value of S2 of t, which is the first term in the numerator of equation 5, is defined over the interval 0 to 2t divided by 3. Whereas, the last term, which is phi 1 of t, is defined over the interval 0 to t by 3. Therefore, while computing the value of phi 2 of t, I have to analyze this for both the time durations 0 to 2t by 3 as well as 0 to t by 3. Let me now therefore write the phi 2 of t as a 3-part expression. I will first consider the interval 0 less than small t less than or equals to capital T by 3. Let us go to the numerator. Between the interval 0 to t by 3, S2 of t is equal to 1 minus of square root of t by 3, and between the interval 0 to t by 3, the value of phi 1 of t is square root of 3 by t. So, the second term, which is square root of t by 3 multiplied by square root of 3 by t, will cancel out to create 1. So, the numerator is 1 minus 1, it is equal to 0. So, irrespective of the denominator, now I can write the value of phi 2 of t over the interval 0 to t by 3 as 0. The next interval will be between t by 3 to 2t by 3. Once again, let us analyze the numerator. The first part, which is S2 of t, is still equal to 1 over the interval t by 3 to 2t by 3. Whereas, the second part of the numerator, which is phi 1 of t, is defined only over the interval 0 to t by 3 and is 0 otherwise. Therefore, in the numerator, the second term reduces to 0 and only the first term of the numerator will remain, which is equal to 1. Therefore, the final answer for phi 2 of t over the interval t by 3 to 2t by 3 will be 1 divided by square root of t by 3, which is going to result in square root of 3 divided by t. And lastly, for values of t greater than 2t by 3, the numerator is completely 0. Why? Because S2 of t for any value of t greater than 2t by 3 is 0. So is phi 1 of t. So, we will get a 0 for any value of t greater than 2t by 3. This is the final answer for the second basis function. Let us now move on to the third basis function. Very similar to what we have done for second basis function, we once again create a intermediary signal G3 of t for defining the third basis function. So, G3 of t equals S3 of t minus S31 into phi 1 of t minus S32 into phi 2 of t. Using this equation, we can now define the third basis function as phi 3 of t equals G3 of t divided by square root of integral 0 to capital T G3 square of t dt. Let me substitute for G3 of t from the above equation. So, phi 3 of t is equal to S3 of t minus S31 into phi 1 of t minus S32 into phi 2 of t whole divided by square root of, it is E3 minus S31 square minus S32 square. Let me call this as equation 6. Now, looking into equation 6, we identify there are 3 unknowns, which are E3, which is the energy of signal S3 of t, then we have S31 and S32. I am going to compute each of them now. Starting with E3. E3 is given by the expression integral 0 to capital T S3 square of t dt. We know that S3 of t is defined over the interval t by 3 to capital T. So, the integral limits change to t by 3 to capital T. The value of S3 of t over that interval is 1. So, it will be 1 square dt. So, it will be equal to t minus of t divided by 3 equals 2t divided by 3. Then I will move on to find S31. S31 is given by the expression integral 0 to capital T S3 of t into phi 1 of t dt. But S3 of t is defined over the interval t by 3 to capital T, whereas phi 1 of t is defined over the interval 0 to t by 3. Therefore, this results in a 0. You can compute and verify whether this is correct or not. Lastly, I move on to the next coefficient S32, which is given as 0 to t S3 of t into phi 2 of t dt. Now, since S3 of t is defined over the interval t by 3 to capital T and phi 2 of t is defined over the interval t by 3 to 2t by 3, we need to now only integrate it over two intervals starting from t by 3 to 2t by 3 and from 2t by 3 to capital T. So, I will retain the part of the expression as it is. Now, over the interval t by 3 to 2t by 3, the value of S3 of t is 1 and phi 2 of t over this interval is equal to square root of 3 divided by capital T. Then we have a plus between 2t by 3 to capital T, the value of S3 of t is 1, however, the value of phi 2 of t is 0. Therefore, this simply reduces to square root of 3 divided by t integral t by 3 to 2t by 3 dt, which reduces to square root of t divided by 3. Right. So, we have now found S31, S32 as well as E3, and let us now substitute all of them back into the equation for phi 3 of t. I am going to rewrite equation 6 here for convenience. Right. This is going to help us in analyzing the values of phi 3 of t. Just like how we have analyzed phi 2 of t over different time intervals, phi 3 of t should also be analyzed at different time intervals. Let us start with that part here. So, phi 3 of t I will analyze over 3 different time intervals starting from 0 to t by 3, then from t by 3 to 2t by 3, and lastly over 2t by 3 to capital T. Right. So, let us now go on to analyze the numerator part. Please note the first term of the numerator, which is S3 of t, is defined over the interval t by 3 to capital T. Phi 1 of t is defined over the interval 0 to t by 3 and phi 2 of t is defined over the interval t by 3 to 2t by 3. So, you have to be very careful while finding the final answer. Let us start with the first interval 0 to t by 3. Between 0 to t by 3, the first term of the numerator is 0. The second term anyhow reduces to S31 multiplied by phi 1 of t, that is a non-zero value, whereas the third part, which is S32 into phi 2 of t, is once again 0. So, the final answer for this interval would be S31 multiplied by phi 1 of t. However, when you come back and check, we found S31 is equal to 0. Therefore, the numerator simply reduces to 0 and therefore, I can write phi 3 of t over the interval 0 to t by 3 is 0. Let us now move on to the second interval t by 3 to 2t by 3. Once again going back to the numerator, S3 of t is defined over this interval and is equal to 1. The second component of the numerator will reduce to 0 because phi 1 of t is only defined between 0 to t by 3, and currently we have a value of t greater than t by 3. So, only the first and last parts of the numerator will be considered. Let us now move on to the last part. S32 we just computed to be square root of t by 3, and phi 2 of t over this interval is square root of 3 divided by t. So, the last part reduces to 1. So, the first part of the numerator is 1, the last part of the numerator is 1. So, 1 minus 1 reduces to 0. So, let us now move on to the last interval, which is 2t by 3 to capital T. Once again, go to the first part of the numerator. First part of the numerator is S3 of t and is equal to 1 over the interval 2t by 3 to capital T. The second part of the numerator is 0 because it does not satisfy the timing constraint. And coming to the last part, we find that phi 2 of t is 0 over the interval 2t by 3 to capital T. So, the second part is 0, the third part is also 0, only the first part, which is S3 of t, is the non-zero part. So, we finally get the numerator as 1. So, it is equal to 1 divided by, let us now come to E3. We have computed E3 to be 2t divided by 3 minus of S31 square, but S31 is 0. So, simply neglect that, minus of S32 square as well. So, S32 we have just computed to be square root of t by 3. So, it will be equal to 2t by 3 minus of square root of t by 3 whole square. So, it will reduce to t by 3. So, the complete equation will be something like 1 divided by square root of t divided by 3. So, when I take the 3 to the numerator, the answer becomes square root of 3 divided by t. This is the final answer for the third basis function. Right. So, that is how you find the basis functions for a given set of signals. Now, since we are also asked to sketch the basis functions, let me do that part here. Now, coming to equation for phi 1 of t, you find that it is equal to square root of 3 by t over the interval 0 to t by 3. So, let me just draw that part here. Moving on to the next one, phi 2 of t. From the equation we find phi 2 of t is defined over the interval t by 3 to 2t by 3 and is equal to once again square root of 3 by t. Lastly, when we come to the last basis function phi 3 of t, the amplitude of that is once again equal to square root of 3 by t, but it is defined over the interval 2t by 3 to capital T. Right. So, that is about plotting the basis functions. So, as a conclusion, we can now say that it is possible to express the given input signal set S1 of t through S4 of t as a linear combination of the three basis functions we just created. Right. So, that is about the conclusion, and that actually is the end of this numerical as well. Well, if you like this video, kindly like and share this video and subscribe to the channel for more information on digital communication. Thank you for watching. Have a good day.